In this video, we'll explore ancient Indian mathematics. Now, much of what we know comes from the ruins from the very ancient Indians because much of their work was done on little black boards that was written with a paint that could easily be wiped off or with flour that was then written on with a stick. And by doing so, in those formats, the work would then disappear afterwards. Now, we do see, though, in the ancient civilizations from these ruins, a lot of explicit work that had to have used mathematics and engineering. For example, in Mohenjo-Daro, that was about 5,000 years ago, we can see a very vast city laid out in a very specific manner that had to have wide streets, a drainage system, canals, all these aspects that definitely used advanced mathematics and engineering. Now, we can also see other texts that do come from the time period as well as writings on different ruins. About 700 BCE, we have the Sulva Sutra, which has geometric rules about how to construct altars, and we see explicitly that it used Pythagorean triples, as well as showed ways to calculate approximate values for squaring a circle and the square root of 2. So you think about the time the Pythagoreans in Greece were struggling with the square root, especially the square root of 2. Here, the ancient Indians are able to approximate it all the way up to about 4 or 5 decimal places. We also see pillars from the empires of that time around 250 BCE that have positional numeral systems written on them as well, something that's important for our current way of doing mathematics. And the Gupta Empire around 400 CE became a major place for people to come and learn, do art, medicine, and mathematics and astronomy. So we see a thriving civilization that's occurring in India as we get into the early CEs. And that leads to a lot of bleeding over of concepts in mathematics and science and astronomy between many of the major civilizations that occur that we think of as being these ancient civilizations that had huge impacts on our mathematics and science. Now, when we look at some of that basic mathematical discovery that was done by the Indians, one of the big things we recognize is a lot of our computations come from ancient India. The positional numeral system was a focus. The idea that how we use the number 0 as both a placeholder and it having properties comes from ancient Indian mathematics. And our compact forms of doing operations, where we don't always show place value, often was first discovered and utilized by the ancient Indians. Within geometry, we see aspects of such as Brahmagupta expanding on Hero's formula for the area of a cyclic quadrilateral, and Bhaskara proved that the Pythagorean theorem could be done through dissection or by using the geometric mean. So we even see, again, concepts that bleed through different civilizations and showing up as well within Indian mathematics. Now, their algebra is often one of the key parts that the ancient Indians were known for. It was written in verse and was in a poetic language because, as we saw, they don't necessarily keep text because texts take a lot of time and resources to be able to construct because there's no way to reproduce easily. So by writing in poetry, they could easily be translated from one person to another by just memorization. The problems were often solved using false position or inversion, but we do see that in those texts that did exist that there was a syncopated version of algebra, which helps lead to our symbolic version that we have now. They also, at that time, would work with irrational numbers like the square roots. Negative numbers were not a problem. They could calculate 2 roots to a quadratic by completing the square, as well as the quadratic formula. And they were actually the first to be considered to devise indeterminate analysis for equations. Now, one of the famous mathematicians and astronomers of that time was Brahmagupta, and he was considered to have been the astronomical observatory in Ujjain, the head of that. And he wrote multiple texts. The one that has a much of the mathematics we consider comes from the Brahma-Sputa Siddhanta. And within that, there's 25 chapters which significantly focus on astronomy, which was then using the mathematics to help him. But there are some key aspects that were explicitly focused on math, such as properties of 0, both that when you subtract a number from itself, it becomes 0. He did inaccurately state that 0 divided by 0 equals 0, but the idea of actually even working with 0 is vastly important to help move us forward with our mathematics. There's also work there for working with positive and negative integers and rules on how to do that. Again, he calculated that area of the cyclic quadrilateral, and he's considered to be the first to construct the quadratic formula as we use today. Additionally, they were able to solve systems of simultaneous indeterminate equations. So very advanced things that, especially that we use in mathematics today in algebra, that helped progress our math. Now, Muhavir built on the work of Brahmagupta when he wrote Ganit Sara Samgra, and it was dedicated solely to mathematics, which was important because at that time much of the work was done for astronomy. It was written in prose and verse, just like many other texts of that time, because that allowed it then for it to be passed on to others without needing many other versions of the text. It had 9 chapters to it that focused on terminology and operations and fractions, area, and many other calculations. It's the first place that we see someone state that the square root of a negative number does not exist, or does not exist as a real number. Additionally, we get terms in geometry that we still use today based on this work, such as equilateral and isosceles triangle, rhombus, circle, and even semicircle. Next, we have Bhaskar, who wrote the Lilavati. The name of it in the book itself has as much to the legend as the works that's within it. It's said that he wrote this book because he first predicted when his daughter should be married. He created a contraption with an hourglass that would then pass the time to the exact day and time she should marry. But when looking at it, one of the beads fell off of her headdress and stopped up the hourglass, and no one recognized it. The time passed, and her marriage didn't occur when it was supposed to. Some places say that they did get married, but her husband died quickly thereafter. And as part of his sorrow, Bhaskar named the book after Lilavati. Now, this book was quite impressive, and it was used for hundreds of years afterwards. It was 79 verses with a wide range of mathematical topics. The way he wrote it, he would actually write some of the prose to his daughter specifically for her to solve the problems. So it's considered that likely he would do mathematics with her, and that she must have, even though it was not necessarily considered appropriate for that time period for women to be doing mathematics. Now, it includes many methods for operations that we use today, volumes of different shapes, trigonometric relationships, solving even some algebraic unknowns, and then properties that are important for enhancing our positional numeral system, enhancing how we work with zero, working with negatives, and even a more advanced value for pi. And like many others before him, he was able to work with a Pythagorean theorem in these problems. Now let's look at some of the operations, both in addition and multiplication, that come from these time periods. Now, prior to the Lilavati, one of the ways that would have been done is called upward addition. In this, we go left to right and we add upward. If a right digit sum is greater than 10, we're going to cross off the previous sum on the left and add 1 to it. So here, when we do this, we're going to say 1 plus 3 is 4. 9 plus 4 is 13, so we're going to cross through the 4 and put a 5 up here. Then 5 plus 6 is 11, cross through the 3 and put a 4, so the sum would have to be 541. Now, then in the Lilavati, Bhaskar gives another method. Here, it's much more like thinking about place value addition. We start with the ones digits and we add them together. Now, when we add the tens, we're going to use a placeholder for the ones digit to recognize that we're now working in the tens. In other words, he was using this in the place of thinking about a 0 being there. Then for the hundreds, we put 2 of those, representing 2 zeros. And then we can add those 3 place value numbers together to get the sum of 541. Additionally, we see a method for how to do multiplication called the lattice method that comes from the Lilavati. Now, many other civilizations had a similar method, so it is important to recognize that it could come from other places, but we see it written explicitly within this text. To do this, we construct our array of an n by n rectangle, and we're going to label the digits on the columns and rows. We're going to place diagonals all the way through from top right to bottom left of each of the boxes within the array. And then we're going to find the products. If we have 2 digits from a multiplication, we put the tens digit on the left and the ones digit on the right of that diagonal. And then we're going to add within the groupings of the diagonals. We carry as needed. So to show how this would work, let's do 256 times 87. So this means I need a 2 by 3 array, and I'm going to list 256 on my 3 columns, and I'm going to list 87 on my 2 rows. Now I'm going to draw the diagonals through, always making sure everything connects. So top right to bottom left. Now let's go through and do our multiplication. 6 times 7 is 42, so 10's on the left, 1's on the right. 6 times 8 is 48, 5 times 7 is 35, 5 times 8 is 40, 2 times 7 is 14, 2 times 8 is 16. Now I'm going to expand my diagonals so that I can add up those diagonal groupings. So if I look at the first one here, that's just 2. Then I do 8 plus 4 plus 5. That's 17, so I'm going to carry the 1. Now I got 1 plus 4 plus 3 plus 4 is 12. I'm going to carry the 1. Now 1 plus 4 plus 6 plus 1 is 12. I'm going to carry the 1, and then 1 plus 1 is 2. That tells me my solution for the product would be 22,272. Now it's important at times to compare the ancient civilizations just to understand where there's similarities and where there's distinctions. For example, when we look at the ancient Greeks and the ancient Indians and how they did their mathematics, the Greeks often were said to have done their math more so for just doing mathematics and understanding the theory. The ancient Indians often were using mathematics to help them with understanding their astronomy that they were working. At the same time, in Greece, just about anybody could study mathematics because it was often done in the agora. Now, when we say anybody, often that typically means the men of that time because of the democratic society and how it was structured. In contrast, the Indian society was set up in a caste system, and doing so meant that fewer people could actually do mathematics, primarily those that were priests. When we look at the mathematics that was done, the Greeks were prolific in their geometry and focused less in their computation, whereas the Indians focused more on computation, likely because of their emphasis on astronomy, and had fewer overall accomplishments in geometry. And again, that doesn't mean there was none. And that same thing, like we don't think that they did nothing other than astronomy. It's just where is more of the work completed. When we look at the types of trigonometry that were worked, the Greeks focused on geometry and the geometric forms, whereas the Indians often focused in the algebraic forms of trigonometry. When we look at how presentations were provided and how problems were written, often with the Greeks, there were as a concise logic-based method for how they would solve problems. It goes with their demonstration of trying to do proof. Whereas the Indians often wrote in poetic and flowery, beautiful verse, and that was because they didn't have the text that they could then reproduce, and so they had to have an easy way, and language was an easy way by writing that poetry that it could be passed from one person to another. Additionally, when we look at how was demonstration done, the focus for the Greeks was on rigorous demonstration and proof, whereas much of what we see from the Indians and when we look at their texts was that they focused more on the empirical results and less on that proof or demonstration. Again, none of these mean that those things didn't exist within one civilization or another, but within the manuscripts and texts that we have access to, these are some of the generalizations that we can see.